Hello and welcome to our first video for the 2020 paper. Here we're just going through the MCQ questions. So to start off, question one, we're looking for which of the diagrams correctly represents the forces acting on the object resting on an inclined plane. So I guess what we've got to quickly think about when it comes to our multi-choice question is what are the forces that we do know that should work on an inclined plane. So first one I like to think of is our FW, or otherwise could be FG, so our force weight or the force of gravity on our object. So we're going to look for ones that have a force pointing straight down or perpendicular with the ground. So not perpendicular with the slope, perpendicular with the ground. So I'm going to rule A out. I'm also going to rule C out because it's pointing downwards and that's not perpendicular. So I've already ruled out two options. The next one, what I'm looking for is the normal force. So our normal force is the force that's preventing our object. So here's a surface, here is our object, is preventing the object from being pushed through that surface. So it would be the force pointing perpendicular to the surface. So let's confirm, all right, here's our normal force here, and here's our normal force here. So both those are still true. So we're stuck with B and D. Now, the other force I'm going to look for is the force of friction. So it's the force that's stopping our piece or our object from moving down the slope. So it's the opposite direction to that. So here we can see our force of friction, F, F, and also here we can see our force of friction. But what we also do have is a force opposite our force of friction in D. Now, the important thing to think about in this diagram or this question is the forces acting on an object resting. Now, this force that I'm going to draw now in blue would be a reasonable force to draw on it if you were going to put a force like this and then neglecting your force weight, because you could think of it as your sine. So the first arrow, this one here, as sine theta multiplied by your force W, and the other blue pointing downwards, that second one could be sine theta, or sorry, cosine theta times your force W. So what you're doing is essentially breaking it up into its different components. Now, my answer for that one would be B. Now, moving on to question 2. The definition of average speed is the rate of change of. So let's go through our options. The rate of change of velocity. If velocity changes, if it's the rate of change of velocity, we're thinking acceleration. So if your velocity is increasing as it goes from like 0 meters per second up to say 2 meters per second, that velocity is increasing. If velocity increases, it's a rate of change, so it's accelerating. So the rate of change of velocity would equal acceleration. So that's not our answer. Distance. Now, distance, our rate of change of distance is average speed, so B is also going to be our answer for this question. Let's just go through the other options quickly. So if we have the rate of change of acceleration, we have meters per second squared. So I like to think back to our velocity question. So the rate of change of meters per second, we figured out as being meters per second squared. So the rate of change of velocity is acceleration. This would end up becoming meters second cubed, and that's not something we measure. Displacement now, some students might have got stuck up between distance and displacement for the choice. What we like to think of displacement, the rate of change of displacement is our velocity. So remember, always think back to the example of going around an oval track. Your displacement is your position from the center. You may run 100 meters from here around the track to here, but your displacement is actually that distance there from your origin. It's not the distance covered, it's your distance from your origin when you think about displacement. So to reiterate, the answer for question 2 is distance. Now moving on to the next one. So question 3, the diagram shows two vectors, vector A and vector B. Calculate the magnitude of vector A, or when vector A is added to vector B. So this is just a simple vector diagram. So draw out your two vectors, vector A going from here and is 12 km, and then vector B is added to it, or sorry, the other way around when we're phrasing it, it says vector A is added to vector B, so we draw it vector B first. So vector B going down 9 kilometers, and then vector A goes towards the right at 12 kilometers. So for simple vector addition, we're going to draw a vector from our origin, and what do we get is a right angle triangle. And so we're just going to use Pythag for this one. So 12 kilometers squared plus 9 kilometers squared is going to get us 306, and then square root of 306 ends up getting us 15 kilometers. So our answer for this one is going to be A. Fortunate thing about this to keep in memory for other questions, which are short response, if you don't have your units, that's not going to be the correct answer. The luxury of MCQs is they should have the correct units. Now, question 4. The diagram shows a current carrying loop moving from one magnetic field to another magnetic field in 0.600 seconds. Here we have our diagram of our magnetic fields. X's, they denote the magnetic field going into the page. And we also note from the region where it currently is, it's 3.00 MT, so milliteslas, and then goes to a magnetic field of 1.5 milliteslas. Calculate the magnitude of the EMF produced in the current carrying loop. So for this one, if you don't have it memorized off the top of your head, you have to go find your EMF formula in your formula book, and then also pick the appropriate EMF formula. So we have to go for our EMF formula, which has got the change in the magnetic flux, but we're not going to do just the magnetic flux. For magnetic flux, we're calculating that as the change in BA over now the change in time. In this situation, we have our change in time as 0.600 seconds. The important thing to think about is your units. This is in milliteslas, so we need to convert that to teslas. So the important thing there is that it's times 10 to the negative 3 for any unit that we have there, as well as for our radius. Our radius is not in meters, it is in centimeters. So we need to remember that R is going to be equal to 0.04 meters. So what we'll have in our EMF formula is equal to the change in our magnetic flux. So what that's going to be is the initial minus the final. And what you're going to note is we're going to neglect in this situation the magnitude of it, so the negative or positive, but we're going to get 3 milliteslas, so I would put 3 times 10 to the negative 3. Our area, I'm just going to write to the side here for our circle, is A is equal to the area of a circle, pi r squared, so pi times 0.04 squared. So I will put the area here multiplied minus by our 1.5 times 10 to the negative 3 multiplied by the area of our circle. So coming back to this one, all over our change in time, 0.600. So if we were to punch that into our calculator, we end up getting our EMF as equal to 0.0000126 in our units and volts. So we've just got to look for the appropriate powers. So it's going to move back 1, 2, 3, 4, 5, and we get 1.26 times 10 to the negative 5. So B is our answer here. So an important thing to flag with all your questions is if you're seeing a question where The major difference between all your options are the powers, so -6, -5, -1. They're probably trying to trick you. So what you need to do is think about, are all my units in the correct units for that formula? So here it's milliteslas. If we were to put that in as just 3.00 and not times it by the 10 to the -3, we'd get a completely different answer. We'd get 1.26 times 10 to the -1, or even 10 to the power of 2. So we've got to be very careful with these kind of questions when you see all the options are nearly the same, but the main thing that's different is your power. So they're trying to get you to think about, are my units correct? So question 5 to question 7 here are heavily reliant on your understanding of the topic, as well as your memory when it comes around to facts and the physics contents you've been taught, as well as some of these laws. So it's heavily memory reliant. So which of the following for question 5 is Lenz's law? So the total electric charge of an isolated system remains constant regardless of changes within the system. To me, this doesn't sound like Lenz's law. This sounds like more or less the conservation of electrical energy in a closed system. The magnetic flux around a current carrying wire changes in proportion to the rate of change of the current. So again, this doesn't sound too much like Lenz's law. It more or less starts heading towards the magnetic flux and starting to think about Faraday's law. C, the direction of an induced electric current always opposes the change in the circuit or magnetic field that it produces. Now, to me, that is nearly Lenz's law to a T. So I'm already not even going to worry about reading D and put C as my answer. But if we're to have a quick look, the ratio of the sines of the angles of incidence and refraction of a wave is constant when the wave passes between two given medias. So this is starting to sound like light refraction and some of our laws of refraction between two media. So again, it's not really fitting with our Lenz law. If we think and recall that Lenz law kind of sits under that kind of magnetic or electromagnetic unit you've been taught. Now, question 6, define the relativistic momentum. The definition of relativistic momentum is, so again, memory, we're just going to go through the options and think what we can get. So momentum of an object, so first one, object when measured is in a Newtonian frame of reference. So in the Newtonian frame of reference isn't quite the answer. That is just a place where everything just stays the same. B, momentum of an object when measured regardless of its frame of reference. Now, that's not true because we know in different frames of reference, momentum can be different when we start thinking about our special relativity. As well as momentum now, or C, momentum of an object when measured in the frame of reference in which the object is in motion. Now, to me, that ticks the box for our solution for 6. So when I think of relativistic momentum, I think of a relativistic frame. So that frame here, if we draw it, we've got an object in motion in here. And that object in motion, be it a ball, has momentum. But it's all relativistic to this frame here. But this frame itself could be moving. And it could be moving at the speed of light or near the speed of light. And that's when we start thinking about our special relativity, like time dilation as well, when we start not just thinking about momentum. Now, question 7, a quantum of any form of electromagnetic radiation is also known as, again, memory, let's just go through the list, a photon, an X-ray, positron, an electron. And we know a quantum of any form of electromagnetic radiation is just a photon. We know X-ray, when we think of electromagnetic radiation, is a portion on our electromagnetic radiation wavelengths. Can be X-ray, visible light, gamma radiation, or gamma radiation should fall under that X-ray kind of grouping. Positron and electron aren't quite going to be our form of electromagnetic radiation. All right, so question 8, we have an object 46 meters above the ground is projected horizontally with an initial velocity of 25 meters per second. Calculate the horizontal displacement of the object at the time it reaches the ground. So for a lot of these projectile motion questions, it makes it very easy if you're able to draw out the scenario and see what's happening. So we have something that is, let's call it a ball is 46 meters above the ground, and it is being projected with a horizontal velocity of 25 meters per second. Now, what ends up happening is that ball is going to follow an arc motion as it goes and hits the ground. And what we want to find out is the horizontal displacement for when it hits the ground. So I like to use my kinematic equations when solving this question. And the first thing I want to figure out is how long it takes for the ball to hit the ground, so going down. We only have one force or one form of velocity or acceleration working on the ball, and that is acceleration going down. And we know A is equal to, 9.8 meters per second squared. There's no initial velocity as well pointing downwards, so the initial velocity is equal to 0, and we're not too fussed about our final velocity. What we're trying to solve for is time. So the kinematic equation we would look for is our displacement is equal to ut plus 1/2 at squared. So what would sub in? U is equal to 0, so we know that cancels out. A is equal to 9.8, times it by half, and we'll just substitute in. So S is 46 meters, that's how high up it is, plus 0.5 multiplied by 9.8 is our 4.9 times t squared. We'll just use our simple algebra to rearrange that around, and we end up solving for t as equal 3.064 seconds. And so what I will end up putting into my calculator now is I know that ball will hit the ground after 3.064 seconds. So I'm just going to do 3.064 multiplied by 25. So our speed times the time, and that will get us our distance, and we end up getting 76.599, and our closest answer is A. And that's the solution for question 8. Moving on, question 9 is again another memory one. I don't want to go through all the choices. So what I give you, or what I'll give you for tips moving forward, is hop onto Plexus Lectures. We have flashcards, which is a great resource where it uses active recall to further solidify that memory and get you ready and practicing to recall information in an exam setting. But if, as we go through it, C is your answer for the list of containing the 6 types of quarks: up, down, charm, strange, top, and bottom. Now, question 10 again is the same as question 9, just a memory test. It's a memory fact. So the force that quarks experience that leptons do not is strong force. So question 11, what we're being asked for is we've got diagram shows an object for object A and object B being projected at different velocities. These different velocities also have a different angle. Now, which of the following statements is true? So there's ways to approach this systematically, and what I'd like to first of all start off with is just check what kind of statements that we need to check, and it will help determine kind of the calculations we're going to do, and probably in what order we can either confirm or deny one of these. So object A has a shorter flight time than object B. Object A has a smaller maximum height than object B. Object A has a larger horizontal velocity than object B. And object A has a smaller horizontal displacement than object B. So I think the first and easiest one for us to rule out or correct is C. So object A has a larger horizontal velocity. So we're going to quickly recall back to SOHCAHTOA. You guys should already have this kind of committed into your memory when you're trying to break down the X and Y components of a projectile. But if we're trying to find the Y component, so in this instance here, or the question specifically is asking for our horizontal, so we're going to do our X component, we know we're going to use cosine. So here it's going to be 10 for that, cosine 45, and our horizontal or X velocity for this instant is equal to 7.1 meters per second. Now the other we have here is we're going to follow the same thing. 13 is our magnitude multiplied by cosine 30 degrees, and we get 11 here. So B has a greater. So first of all, we've ruled out object A because object A does not have a large one. The next one I'd probably look at ruling in or out is probably option A, because if I can figure out the flight time, I can then figure out, okay, the maximum height, and then as well as figure out the horizontal displacement of both objects. So we're going to do the same here. We need to figure out the vertical or the Y velocity for us to then be able to calculate the flight time. So same as before, but we're going to use sine because on our triangle, there's our inside angle. Our hypotenuse is our magnitude of the projectile. Then we have our opposite here and our adjacent. So if we use SOHCAHTOA from memory, that should help you bridge the gap if you don't have that committed to memory. So here we're just going to do 10 sine 45. We should already know with a 45, 45, 90 triangle, this is going to be the same as our X, which would be 7.1. Now the same goes here. We've got 13 sine 30. That's not going to be the same. So when we punch it into our calculator, we get 6.5. So right now we've got our vertical velocities in meters per second, just making sure you remember your units. In this case, it's an MCQ question. Units are either going to be on the options to choose from, and it's not a short response. All right, so I'm going to use this formula here to figure out the time. So I'm going to use VU plus AT. So the reason I'm using this formula is the way I'm thinking about this projectile is the path it follows will be an arc. And I know the initial velocity, U here, but I also know the peak, which is in the middle of our arc, halfway here to halfway here, is the exact same amount of time. But the velocity up the top here, V, is equal to 0 because it's the turning point on the arc. And I know what A is equal to. It's equal to negative 9.8. So from that point forward, I'm just going to erase this and clean it up. I can substitute into this equation and rearrange and solve for time. I'll only get this small segment here, but I can times it by 2, and it'll get me the total flight time. So I'll clear this up now. So for option path, or I guess object A, we have V0 is equal to the initial velocity of 7.1 minus 9.8 because gravity is working in the opposite direction, multiplied by time. We can rearrange that and we get time is equal to 0.72. We're going to multiply that by 2. That ends up getting us our total flight time of 1.44 seconds. For object B, we're going to do the same. 0 is equal to this time 6.5 for our vertical initial velocity minus the 9.8 t. T ends up being rearranged to be 0.66. We again times that by 2 for the total 1.32. So A in this case has a longer, so we've already ruled out this option here. Now we can do object A has a smaller maximum height than object B. So to rule this one out, we want to find out how long, if I draw that arc again, not quite complete, but what's the displacement or the maximum height here? So again, we can use another kinematic equation to figure that out. So the one that I would use would be displacement S is equal to U, initial velocity, T plus 1/2 AT squared. And what I would do is substitute all the values we know here into it, but I'm just going to highlight it here. The time I'm going to use is the time we calculated here, the half, because that's the point at which it reaches the maximum, at that half point. If we were to put the whole time in here, we'd find the displacement in the vertical would be 0 because it'd be back to the same vertical displacement. So I'm not going to bother showing all the steps for this one, but if we were to punch that into our calculator, what we end up getting is the displacement for A as being, so I'll go AS is equal to 2.57, and that would be meters if we're keeping track. B ends up being S is equal to 2.15 meters. So in this case, B has a smaller maximum height than object A, so we've ruled that out. And we're only left with D as our true statement. We can check that by just doing the 7.1. So our horizontal, or the x velocity, multiplied by the total time for each instance, and then we could prove that there. So they're the steps working through for question 11. It's quite a long-winded MCQ, but it's one of those ones you've just got to keep in mind. Now, moving forward, question 12 is very much just a memory question again. So all you've just got to know is that for which of the following is one of Kepler's laws of planetary motion, is that all planets move about the sun in an elliptical orbit, having the sun as one of the foci. So I'll reiterate this again. We have some really good flashcard resources for students to use on Plexus Lectures, our online learning platform. So we highly recommend jumping on using those because it will help you with a lot of these memory questions. So question 13, Rutherford atomic model describes an atom as, so your answer here should be with a small dense nucleus surrounded by orbiting electrons. So option B. Another memory choice here. So select the list that contains only gauge bosons. So what we're going to go through is we should think of either, okay, a gluon, photon, Z boson, and W. So that is going to be C here. So with list kind of MCQs, the tip that I would go through is go through and tick off what you do know. So if I know, okay, that is going to be one of my options, it's got one of the particles or one that's contained. Okay, cool, a photon. Do I have any of the others? Here's a photon here. It's not quite looking like D, nor is it looking like B. Now, I've got to know a little bit more kind of in-depth detail about it. So it would be tossing up between A and C. But there's not much else you can really do for a memory question than continue practicing seeing more multiple choice questions. All right, so question 15 here is a fairly straightforward question with calculate the orbital period of a satellite traveling on a 3 × 10⁸ meter radius orbit around the Earth. So first thing is we've got a orbital kind of question, but the main thing I want to make sure I flag is that it's in meters. So I don't need to convert any of my units right now. So the formula I would be looking for is something that will give me the period of an orbit, the mass of the planet I'm orbiting, as well as the radius. They're the kind of information I've got that I can put into my question or put into the formula. So the formula we end up grabbing is t squared over r cubed is equal to 4 pi squared over g m. So g is our constant here at 6.67 times 10 to the negative 11. M is the mass of our object that we're orbiting, and in this case it's Earth, and that too is in the formula book, and that is 5.97 times 10 to the 24. And we also know the radius that this object's orbiting at, r is equal to 3 times 10 to the power of 8. And then from there, we can rearrange and solve for t. So some students like to go about these questions in different ways. Substitute all those values into the equation and then rearrange and solve. My approach is go forward and rearrange the formula to the term that you're trying to solve for. So we're trying to solve for t squared, or sorry, just t by itself. So I got to think of how can I rearrange that formula algebraically, and if at this stage you guys should be able to move through it quite quickly. So the first thing you're going to move is that r to the power of 3, and it's going to be multiplied, and then I'm going to get rid of that square. So the end solution looks a little bit like this. 4, clean that up, 4 pi squared on g m multiplied by r cubed. And then from there, you can punch that into your calculator, and you've got to remember what type of units this question is going to yield. Your SI units, when putting it through with your G value, has seconds in it. So what we end up happening to get is equal to 16361 0. Sorry, I'm missing a 6 here. 6.87 seconds. So from there, what we need to do is end up converting it down into hours. So seconds to minutes is divide by 60. Minutes to hours is divide by a further 60. And we end up getting our time is equal to 4.47 hours. And then our question looks like it has two significant figures. So it goes down to 4.54 times 10 to the power of 2. So we're left with option B. Now moving on to question 16. According to the theory of special relativity, the concept of simultaneity is best described as, so this is just best described as when two events observed to happen at the same time in a particular frame of reference. So from here, that's going to be our option C. Going on to 17. So the definition of a magnetic field. Again, we're just going to, the tip is read through all the options you have there. Either you have something like this committed to memory, or you're trying to rule out things that are, first of all, outrageous of a choice, and then rule in what is the most reasonable solution. Because at the end of the day, if you have no idea and you're guessing, you might as well try and guess a little bit more correctly, or have that more educated guess. Take it from a 25% chance down to, say, a 50% chance, or even a 33% chance. It's better than a 25% chance if you know something is definitely incorrect. So for this choice, it should be option D, so a region of space near a magnetic electric current or moving electrically charged particle in which a magnetic force acts on any other magnetic electric current or moving electrically charged particle. So D. So question 18, let's go through. So calculate the initial vertical velocity of a projectile with an initial velocity of 68 meters per second at an angle of 51 degrees up from the horizontal. So this is very similar to some of the work that we did in the previous question. I believe it was question 11. So let's draw the situation out. Our magnitude or initial velocity is 68 meters per second, and it was at an angle of 51 degrees. So we know we can either have it committed to memory, or we can recall back to some trig functions and realize we're going to use sine because we have the hypotenuse and we're trying to find here the vertical velocity, which is the opposite. So SOHCAHTOA is sine. So we're going to do here the initial velocity or the hypotenuse, 68 sine 51. Punch that into our calculator and we're going to get 52.84. And again, think your units, that's in meters per second. That's going to closely round to 53 meters per second, so we're left with C. Now, question 19, a solenoid with 24 loops of wire produces an EMF of 36 volts during a magnetic flux change of 0.3. Calculate the period during which the magnetic flux varied. So with this, let's think we're working in the magnetic kind of unit. So I would flick to my formula book, have a look at some of the formulas there if I'm uncertain, and think what kind of variables do I have and what ones or what formulas have those variables that I've been given or I'm trying to calculate. And typically that will point you in the direction to use which formula if you are, if you are uncertain. So we're going to use our EMF formula for a coil. So EMF is equal to N, which is for the number of loops, over the change in magnetic flux, over the change in time. So it's how much magnetic flux ends up changing in that period of time. We know, I'll tick off what we know or has been given. We've been given the EMF, which is 36 volts. We've been given the number of loops or coils, which is 24. And we've been given the magnetic flux, which is 0.3. So again, my tip is I like to rearrange my formula into the term that's unknown, which is the change in T, and then solve for that. So the change in T ends up being able to be solved through, if we rearrange our formula, I would move EMF, first of all, divide by N as equal to change in flux over change in time. And then you want to get the flux over to the other side. So that ends up being your change in flux. You could do it over in brackets EMF over N is equal to your change in time, or you could neat it up by doing the inverse of down here, and you end up getting change in flux multiplied by N over EMF is equal to the change in time. And then punch that into your calculator, you end up getting your change in time equal to 0.2. Remembering our units is seconds, so we're left with option A. Okay, so for our final question, what we're looking at, or what we've been asked to do, is calculate the frequency of light that would be required to eject a photoelectron at a velocity of 1.9 times 10 to the 6 meters per second from a metal plate with a work function of 4.73 electron volts. So we're going to use our formula E, that's not me, E, K for kinetic energy is equal to HF minus W, which is the work energy required, H being Planck's and F being the frequency. Here we've been given some variables, our velocity, and we've also been given the work function, which is 4.73 EVs, electron volts. What we need to remember is that if we're using Planck's constant requires us to use joules, and same goes for if we're going to calculate our kinetic energy in joules, so too must our work function be in joules. We can't have a matching or a mismatch of our energy units. So what I will first do is convert my 4.73 electron volts to joules. There's a conversion in your table, so it tells you that one electron volt is equal to 1.6 times 10 to the negative 19 joules. So I'm just going to do that, multiply it by the 1.6 times 10 to the negative 19. I end up getting 7.56 times 10 to the negative 19 joules. So cool, I'm happy with all my units across the board. The next thing is I want to be able to throw this into my formula, which is the velocity of that ejected electron. So what I can do is recognize that EK, or kinetic energy, is also equal to 1/2 mv squared. We're given the mass of an electron in your workbook or the formula book, so you'd go hunting for that, find out the mass. But then let's substitute these two into a formula. mv squared is equal to hf minus w. Again, I'm just going to go with, I'll rearrange the formula first and then substitute everything in my calculator, and then I can solve for it. So I'll move the w over first. I get 1/2 mv squared plus w. Then I'm left with that f by itself, which is our frequency of light. So then I'm going to divide this all by Planck's constant. We get left with the frequency. Punch my variables into the calculator. Remember what you're looking for. You've got to go into your formula book and find the mass of your electron that has been ejected. And what you end up yielding is 3.6 times 10 to the 15 hertz. So that ends up being option D. So that's going to conclude all 20 questions, or all 20 MCQ questions for the 2020 physics paper. Thanks.